Okay, so we're going to talk about the file system. The file system is somewhat similar to the memory management. If you think about the memory and also hard disk, the secondary storage, which is hard disk or solid state drive, all these are storage space. You think about the storage, and I don't think I mentioned that, but there's actually hierarchical structure for the storage. This look like a kind of pyramid. Okay, let me actually just write over here because there's more space. So if you take a look at the structure of the storage, it's just like a pyramid. And on the top of the pyramid, we're talking about the registers. Okay. Now, register is the fastest storage, actually, in terms of the CPU access speed, because mostly registers are actually in the CPU, and some of the registers are in the I/O devices, but the registers for the computer system are in the CPU. And then the next level we're talking about is the caches, in the CPU or close to the CPU. And then we talk about the main memory. Okay. Or random access memory. Now, below the main memory, we actually talk about some kind of secondary storage, like a hard disk, magnetic disk, maybe SSD. SSD is actually a little bit higher than magnetic space. Okay, so you can say SSD over here, and magnetic disk. Okay. Let me erase that one. And then down below, we may have probably something called optical disk. Something like your DVD, your Blu-ray DVD or something like this. And the bottom is sometimes the magnetic tape. Okay, magnetic tapes. Now, in terms of access speed, register is the fastest. Um, um, the magnetic tape is probably the slowest. Okay, so in terms of speed, it's fast over here, and it's getting slower as we go down to the bottom. But however, in terms of the storage space, the size, it's small. And that's the largest. Okay. Now, there's a line in between. Above this line, we call these storage volatile storage. And then below that line, we call the non-volatile. Now the difference between these is the volatile storage is actually some type of like a temporary storage. So like a memory, you can store your data, your file, your program into the memory space. And then when you actually turn off the power and then turn the power back on, everything in the memory has been wiped out. Okay. Now, the non-volatile storage is actually kind of storage space that that can keep the data for a very long time. So if you save any data into the non-volatile storage, like a hard disk, your solid state drive, then even if you turn off the power and turn the power back on, everything stored in the non-volatile storage are still there. So that's the major differences. And so typically, when you actually, because the volatile storage tends to be faster, so like a memory. So if you try to run any computer program, you want to load the program into the computer memory. So then the CPU can start to actually access the instruction in the memory, to fetch the instruction in the memory. But non-volatile storage is relatively slow, like a hard disk. You know, you basically store the data in the magnetic tape. No, I'm sorry, magnetic disk. And if you try to locate any data on the magnetic disk, you have to rotate the disk to the right position. So make sure your read and write header can actually point to exactly the location in the magnetic disk, and then start to read the data. So that involves some kind of a mechanical movement, which is actually fast. For hard disk, you can think about a speed of 70 to 100 called rotation per minute, RPM. 7,200 rotations per minute. Every minute you can rotate 70 to 100. So that's a minute. So if you think about how many rotations per second, you can divide this by 60, right? So it's still like more than 100 rotations per second. So it's pretty fast. Okay. However, no matter how fast the mechanical movement is, it's still kind of slow comparing with the electronic signals, you know, transmitting in a while. So that speed is almost like a speed of light. So that's why you cannot compete. So that's why the memory access is much, much, much faster than the secondary storage access. Okay. When you think about this, you can think about like it's a 1,000 or like more than 1,000 or 10,000 faster than the hard disk access. So that's why the non-volatile secondary storage is basically used to store your file. But good news is that it can store a large number of data, because non-volatile storage tends to be larger, much, much larger than the memory. So when you actually use the computer system, you can purchase a memory up to like 16 gigabytes or like even 32 gigabytes. And for actually most recent PC, you can get up to like 64 gigabytes. That's pretty big in terms of memory size. However, when we talk about the storage, like a hard disk, even like a solid state drive, you can actually easily reach up to like a 1 terabyte, which is actually about it's probably like a 1024 gigabytes. 1024 gigabyte. Okay. So that's much, much bigger than 64 gigabyte, right? And then when we talk about like a magnetic disk, like a hard disk, the traditional hard disk, you can easily reach like even 12 terabytes, 8 terabytes, 6 terabytes, 12 terabytes. That's much, much bigger. So you can actually use this as storage, okay? And so in modern days, people try to actually back up your data. Typically they use the hard disk, like a magnetic disk, using the network drive called the NAS. Okay, so the network drive allows you to actually put a couple of actual hard disk in there, and then you can create some kind of redundancy, so you can actually increase the the reliability of the data. So even if one of the hard disks goes down, then you still have the data in another hard disk. Okay, so this is pretty good. And also the magnetic tape, they're much, much bigger, even bigger, much bigger than the hard disk. But the access to the magnetic tape is much slower. Okay. And also one bad thing about the magnetic tape is it's not a random access, because if you try to access, find a data stored in the magnetic tape, then you have to make sure the location of this data. And then you have actually rotated the tape to the right position. Now remember, if you ever used a music tape, I don't know whether you have used a music tape. That was very popular 20 years ago, like a Sony Walkman, right? It was really popular, and you can actually purchase a music tape, and put in a Walkman, and you can start to listen to the music. But when you search for the music, you have to make sure where you are, because when you play the tape, you can actually, the tape could rotate. And if you search for the music that was already played, you have to backward the tape. You have to fast forward the tape or backward the tape to actually, rotate the tape to the right position. So it's slow. However, the magnetic tape are still used in many big companies. They use the magnetic tape to back up the data, like create some kind of archive uh, data, archived data. So if you want to store the data, so you don't want to delete the data, but you are not likely to use the data, so you can archive them and put in the magnetic tape. So for most of the company, so they have to do this because it's a law. Like many by law, many companies have to keep the emails for up to like 3 years or 5 years. I forgot the date, the years, but you have to keep a email, in some safe place in case that the federal government want to audit it. Make sure that you still have your email correspondence. Okay, now back to the file system. So now we're going to talk about, for the memory, we talk about the memory management, right? Now, for the hard disk, we're talking about the file system. So which basically talk about how you're going to store the file in the hard disk. The file system, many times we use FS, is an integral part of every operating system, just like your memory management. Okay, so here's the operating system. So there's a whole bunch of different components. One is the process management and memory management, and then the file system, and then there's a I/O system. Okay. So a file is a named collection of information managed on the secondary storage. Okay, by FS. Okay, so the user can view a file as a single abstract unit of data storage and access the file contents using high-level operations provided by the file system, by the file system's interface, actually. Now, the idea for the file system is it wants to provide the interfaces and so the user doesn't have to know the specific characteristic of underlying storage devices. Because here's the deal. If you try to store the data, your file, into the hard disk, you don't know what, you know that the file is stored in a hard drive, okay? Or your computer used a solid state drive, and you know the data is stored in the solid state drive, okay? Now, the way that the data are stored in the hard disk and the solid state drive is different, okay? Because these are two different physical medium. Now, the file system, the purpose for the file system is to hide the details of this storage, but just provide the user some kind of abstract view, okay? To provide the abstract view, okay? Now, depending on the file system, a file can be viewed as an unstructured string of bytes or a series of records, okay? So the file a file are stored in the hard disk in different kind of format. One is called unstructured string of bytes or a series record. So when you talk about record is a structure related to data item, possibly different data types. So you can think about the record as a table, okay? So the data can be stored as a table. Now each table has different field, and if you want to store the student information, then you have a student ID, student name, and student GPA, phone number, address, and then you have each individual student, right? So you have a John, Mary, or whatever. So then each individual student has a different name, different address. So that's a record. You can store as a record. So now once the computer system provides a different way to store the file, and then the operating system need to provide access methods. Okay. An access method is a set of operation provided by the OS as part of the user interface to access files. Okay. So when you access the file, you want to hide the detail, right? Okay. So the most common access method is sequential. If the data is actually stored as using certain kind of format, and then you can access the data sequentially, one after another, from the very top. Okay, and the FS, the file system, maintains the current position within the file, and each read-write operation access the next n byte. So the file looks like a list of blocks, or you can say list of a record. Okay. Now, the file system can start to read the data at the very top. And then you can say this is block 0, 1, 2, 3. So you can actually read the data block by block. Okay. So each block contains certain bytes. Let's say n byte. Okay. So then you have n byte, and then you're going to have 2 n byte. So another n byte, n byte, n byte. Okay. N bytes. Okay. So okay. Or the file can be listed as a record in terms of record. The difference between bytes and a record, you can think about record as each of the data, like a student information. So the record actually basically logically structure the file. But byte string oriented, that means you actually organize the file into like n bytes, a block of n bytes, another block of n bytes, another block of n bytes. You can think about this like a paging in a memory management, right? So the paging using the fixed size. Okay. Now the recorder, because you logically allocate the data, so the access should be relatively easy because you know the contents of the data. Okay. Now here, let's talk about a couple of different access methods. Okay. As we mentioned that the FS, the file system, presents a logical view of files, the logical view of the files to the users. So when we actually say I'm a person who actually create the file and store it in the computer system, I would like to treat the file as a kind of document, right? So for example, like a Microsoft Word document. So I can write something in the document and treat the file as a document. So the document can be show up as each page by page. That's a logical view. That's a logical view. That's the view we would like the file to be, right? That's a logical view. However, how the file is actually stored in the computer system, that's totally different. Because eventually, the logical view is you always think about like this Microsoft PowerPoint. When we see this, each slide, it's a logical view. So you can see the diagrams, you can see the images, and you can see a lot of actually good things over here. Now, how this file is actually stored in the computer storage, that's completely different. That's completely different. Okay. So the bottom line is all the files actually are encoded into a binary numbers, right? Like a 0, 1, 0, 1, 1, 0. It's a binary sequence. And you basically store the binary sequence in the hard disk. Okay. So it's actually binary sequence. So when you actually, when a user actually store the data in a computer system, typically they don't want to know what kind of format you actually use to store the data, right? If you only the computer scientist, they want to know. The user, they don't know, and they don't even care. So why I want to know which data, which part of the document is stored in which particular location in the magnetic disk. That's basically the job that the operating system is doing. The operating system is basically hide the ugly part of the hard disk and only show user a very nice view of the file. So the access method, there are a couple of different access methods. One is each file is named, actually is a named collection of information and is recorded in the directory structure. Okay, so like this. This is 1, this is 2, this is 3. These are 3 actually. Now the first one, so is recorded as, for example, like a fixed size data. Okay. Okay. The second one also. And the third one, each file is record a block, and each block has different size. Okay. So you can actually depend on the different way the file is stored. And you need to treat them differently. And once you actually store the file in certain format, the file system need to provide a uniform interface to the file. A uniform interface to the file. For example, if you want to create a file, so if you want to actually create a Microsoft Word document and store your homework assignment, then you need to, the operating system file system, FS, gonna create a command called create. Okay. And also, if you want to actually, open an existing file, which is already stored in the hard disk, and that was created by you yesterday. So you want to actually use the command called the locate to locate the file and then open the file. And if you say, I don't want this file anymore, I want to delete the file. So you need the operating system FS file system should provide the delete command. Now this command should be very easy to use to the user. Okay. Now when you delete the command, you basically delete the data in a different location in the hard disk, right? So, but the user doesn't have to know that. All they need to know is the file I just created was deleted. Okay. So now, depending on the different type of data, now some of the operating system provide something called unstructured string of data, and then so they need to actually create, read, create, locate, delete, all these command based on this type of data. It's a byte string oriented data. Okay, so the data, the file is stored as called a byte string. It's kind of like a fixed size bytes, another fixed size bytes. They are all the same size. Okay, or if the file is stored as a sequential record, then you need to provide a read and write. Okay, read. Now, from the user perspective, I just want to have a read command to read my file. Now, but underneath the computer system, because the file is stored in a different format, so some is byte string oriented, some is sequential record oriented. So the meaning for the read and the write, the meanings for the read and write is different. Okay, so the read and write, the implementation for read and write for byte string oriented data is not the same as the read and write command for sequential record oriented. So, and then there's another type, it's called direct record oriented type of data. And then you need to implement its own version of read and write. But the user doesn't care. The user just wants to make sure, okay, you just provided me a uniform interface so I can use it. Okay. So now, so if you, for example, for byte string oriented, so you can sort of, the operating system maintains the current position. Okay, so the data is actually stored as fixed size block. It's called, fixed size number of bytes. So, for example, the current position is K. Okay, so then if you want to, read the file, say read. Okay, then you just need to specify, okay, currently it's in the position K. But if I want to actually finish the reading of the position K, then I jump to the next position, which is K plus 1. And start to read the next one, and the K plus 2. So I just keep reading the data one after another. because I know the file is stored as fixed size bytes. And then I just need to actually specify which, what's the position. The position is recorded using the numbers. The first n bytes, the fixed size bytes is called, the number is 0. The second was number 1. Third one is number 3. Just like page, just like a page in the memory. Okay, memory management. Okay. Now, if you use a sequential record, okay. Now, sequential access is supported by maintaining the current position, which is very similar to the byte stream. That's a sequential, but it's a record. Each of these is a record. Okay. Similar to the read-write operation, always access the next record n. So, for example, that's a recorder number n, and then the next record is n plus 1. So instead of like the bytes, okay. So technically it's very similar. The only difference is the bytes, it just actually cut the file into the fixed size, like n bytes. Like if you cut the file size into like 100 bytes per block, and then you have a 100 bytes, another 100 bytes, another 100 bytes, and you don't care the contents of the file. But the recorder is different because each block has basically record a specific data. Another block record a specific data, just like a student recorder. So this is student 1, another block is student 2, student 3, but they represent different students, so they are meaningful. But technically, it's the same as the byte stream because the recorder size is also the same. Okay, so you can view the sequential record as a special case of byte stream. It's also a type of byte stream, but each byte stream has some meaning. So you can actually do this, and you can record it, and you can actually jump. Say, currently it's a record number 5, and then I want to record I want to read the data at the recorder number 100. So currently it's a record 5, but I want to jump to record 100, and you can easily do this, right? Because if the recorder size is, let's see, if the recorder size is a fixed, for example, let's see, let me take it back. So let's say if the recorder size is n, so the current record is 5. If I jump to 100, record 100. So all I need to do is, there's actually 95 records, right, in between. So each record is size n. So I just need to jump 95 times n. So then I can directly jump to 100, the record 100, because I just need to skip like a 95 times n bytes. Okay. So it's pretty simple to jump. And also you can do the search. Okay. That's basically both byte stream and the sequential record are fixed size. Now the third case, if you want to store the file, if the operating system also support the file format as some kind of a variable size, okay, if you want to store a variable size, so in that case, the recorder should be recorded like this with variable length records. Each record started with record length Li. So the first one is L0, L1, and the ith record is Ln. So the L0 basically tells us what's the record length. Okay, so then that's the length, and that's the length L1. So you know that the L0 and the L1 are different. L0 may contains 100 bytes. L1 may contains 200 bytes. But you need to actually specify what's the size of this record. Once you know the size of record, the operating system, actually file system, can actually follow this size and jump to the right position to access the next record. Okay. So for example, if I say I start from here and L1, L0, if the L0 says 20 bytes, so I start from 0. So then it will be 20 bytes. And then L1. L1 says 25 bytes. And then I'm going to jump to, what's the next one? 20. I start from 20, but the size is 25. So I'm going to end up to 45, right? 45 minus 20, that's 25. So that's the next one. And the L2, it says 100 bytes. And then I'm going to go all the way to 100. Oh, I'm sorry, 145. So I can actually do this and locate the next one. But the drawback is if you want to locate the record at like L10, so you cannot jump to L10 because you don't know what's the size for L0, L1, L2, all the way to L9. So you have to actually follow the L0, jump to L1, follow the L1 size, jump to L2, and then follow the L2, jump to L3, and all the way jump to L9, then you can jump to L10. So you cannot skip because each record has different size. So you cannot skip. That's the drawback. So there's no way you can jump like a fixed size, fixed length record. So you can say, okay, here's a record one number 10. I can jump to number 100 because I know all the record in between has the same size. But with variable length record, I cannot do this. Okay, so that's the that's basically gave you some various different view of the access methods. So the operating system file system going to provide a uniform view of each of the command: create, locate, delete, open, close the file. So you can create, but underneath the implementation is different, depend on the how the file is stored. Okay, just let you know that. Now for each of the file, you can actually find a different file types. Okay, so each file, every file consists of two parts. One is the data part. That's the area that you actually store the data. And then the other type is called metadata. Metadata does not store the data for this particular file, but store the information about this file. Okay, so the data is a portion of the file visible to the file user, because if you do your homework and store it in Microsoft Word document, and the data basically contains whatever you typed as a homework. So it contains your homework. Now, the metadata is the information about the format and organization of the file's data, and generally stored in the file header. Okay, so for each file, when you store the file in the hard disk, the file contains two parts. The first part is a file header, and then the data. Okay. The user normally don't see the file header. You cannot see the file header. Okay. So all the user see is the data itself. So the file header is only visible to the file system. And now you have various different files, right? So if you sometimes you have an executable file because you compile the program. So this executable file contains all the instructions. So the computer system can execute the instructions to perform the job. That's an executable file. And there's also some kind of a document file, like a Microsoft Word file, or your plain text file, or sometimes it's a compressed file. So you have too many different type of files. Okay. Now, how does the operating system file system know which file is which? Because if you find out, oh, it's a Microsoft Word file, the operating system is going to trigger the Microsoft Office to open the file, because other software cannot open the file. Now, if it's an executable file, then they try to actually run this file, execute, perform the job. So you have to have somehow some way to tell what type of file is, okay, for each file. So in this case, there's in the file header for each file, there's something called a magical number. Okay, the file system gonna check the file header and check a specific location that the stores a number. That number is called magical number. Okay, it's a very short sequence of characters at the start of the file header, and this is used to identify the file type. In another word, for different file type, the magical number is different. Okay, but normally the users don't see this magical number. It's actually only visible to the file system. Okay. So the file type in turn determines which program are allowed to access and interpret the file. So for example, the operating system will allow only properly compiled and linked binary file to be loaded into the memory for execution. Because if you try to execute a Microsoft Word document, it's not going to work. The Word document is only allowed to be opened by Microsoft Office. So the magical number is the key. There's another way to tell the different type of file, and that's called a file extension. Okay, file extension is a sequence of one or more characters following the file name. So if you create a file called My Homework, now extension is normally, a kind of character after the dot. Typically, the extension file extension is well defined. So if we use the extension like DOC, not every document can use the extension DOC. Mostly only means Microsoft Word, right? Microsoft Word document. Or in modern days, you use DOCX. Okay, that's a newer version of Microsoft Word. Now, if you want to actually create a plain text file to open with a notepad, then typically what's the extension?
.txt.
.txt. Okay. Now for executable, typically you may have like a exe executable or .com. Sometimes .com is also used for executable. Okay. So that's a file extension. File extension, it's also used to differentiate between the different types, file types. Okay. However, there's one actually drawback with file extension, because file extension is visible to the user. It's an extension, the existing file name. So the user can change it. That's really bad. So if you create the using Microsoft Word and you create a file called myhomework.doc, and then I can change .doc to something else. Okay. In that case, I changed the extension, file extension, but I did not change the file type. It is still a Microsoft Word document, but you change the extension to .exe or .txt, which is kind of confusion, right? It's kind of you're gonna cause some kind of confusion. But magical number, so eventually magical number is still the important part. So usually use the magical number to tell what is the file type. Extension is, so this from this perspective, extension is called some kind of like a weak form of file typing. It's just make it easy for people to tell what kind of type is this file. But it may actually mislead you if someone deliberately changed the extension from .doc to .exe, then you will be fooled. So still, magical number is the only magical number that tells the file type what the file type is. Now extension is kind of like addition. So typically the file extension should be consistent with the magical number. If the magical number say it's an executable file, then typically the file extension should be .exe. And if the magical number says it's a Microsoft Word document, and it should use the extension DOC or DOCX, depending on which version of Microsoft Word you actually used to open the file. So that's just to give you some kind of addition. Sometimes it's very convenient. Okay, if operating system see the file extension, they just automatically gonna trigger the corresponding program to open the file. Okay. Now here, I try to explain this, but if you actually read the Zybook, it will give you a better, explanation in terms of how these file extensions magical numbers works, because the Zybook gave you some kind of, some kind of like a visual things, like some give you some kind of animations, so you can see how this actually works clearly. But here, let's explain some of the different things to tell what's the difference between the different file types. Now, typically, when you actually write to your source code, like using Java or C++ or C language, that's a source code. And then you compile it, you create an object code, right? And then you link the library and link the other object code. You could basically create some kind of called a load module. The load module basically combines everything. Okay. Now, the load module is executable. It's an executable file. You can directly double click it, so it will start to run. Okay. Now, typically, this magical number, a load module consists of executable binary code. Okay, that's executable binary code, program data, and the relocation information, and the various other tables over here. Other tables. Okay, so the file header contains the meta information, metadata. That's the file header. And at the very beginning, there's a magical number here. The magical number X tells the operating system, file system, saying that's an executable file. Okay. So this is a the magical number uniquely identifies the specific format used in the file. Okay. So the load module was produced by a linker from an object module. So when you actually do the compile, you create the object module, and then you link all the object module and also link with the library of this particular language, then you create the load module. So then the object module has a different magical number. Okay. And it also has a file header. Okay. So the each object module was produced by compiler from source module. Okay. Like in this case, the source module is program C. This is source code using the C language. Okay. And the source module also has its file head, and then here's the source code. That's a C language code. Okay. And this is not visible. The file head is not visible to user, only can be seen by the file system. Okay. So this just gave you some kind of explanation. Now, however, the file extension somehow tells you what kind of file it is. .exe, that means executable. .o, that means it's object of module. So if you use like a command line compiler for Java, like using Java C, once you say Java C and then space any Java file, and once the compiling is successful, you will see that the compiler actually created an additional file called java.o. That's object file. Okay, that's it. Because you know it's an object file because you can see the extension, which is .o, file extensions. You don't see the magical number Y. You don't see the magical number Y. So that's why extension is good. It give users some kind of idea what type of file is this. It's a .o file. Okay. Now, if you see .c file, that's C language. That's a source code. However, this file extension is very vulnerable because everyone can change it. You can change program.o to program.exe, and then the file system going to misinterpret this and try to run it, and it doesn't work. Okay. Also for the C. So for example, you can change the program.c to change to program.txt. Okay. But you change the file extension. You still don't change the magical number Z. So the file type is still the source code for C language. Okay. But if you change to program.txt, that's going to cause some confusion for the compiler. Okay. Now, depends on who actually create the compiler. Some of the compilers are very smart. So even though you try to compile a program .txt, and the compiler say, oh, it's txt, some of the compiler going to say, well, it's a txt, it's not a source code for C, so I'm going to actually give you error message, say that's not a C language. That's a stupid compiler. But a smart compiler, if someone actually, even though they will not be fooled by this file extension, but they will just check the magical number, say, oh, the magical number say it's still the source code. Let's try to compile. And it's actually compiled well. So it actually generates the program.o file. So even though your file extension is not .c, some of the compiler, which if the creator compiler build some kind of intelligence in there, so the compiler can tell, oh, it's still a C file, even the file extension says it's not a C file, it's a txt file, the text file. Okay, so that's the difference. But this is really going to cause some confusion. Okay, so a user can change the file extension and present the file as an importer to the compiler. So the compiler, some of the compiler could reject the file, or some of the compiler can attempt to compile, and it's successful. And in this case, the compiler may send you the warning, say, well, your extension doesn't say it's a C file, but it's actually a C file. Now, some of the operating system, they realize the file extension may potentially cause some problem. So they actually make the file extension invisible. Okay. So so they make the file extension invisible. Like a Microsoft Word, Microsoft actually operating system, like a Microsoft Windows 10. So they actually so Microsoft actually Windows 10, it's kind of like a different, so they have, if they use the prompt, the DOS prompt, the prompt may actually see, you actually see the extension. But if you use the actual Windows Explorer, the graphic, the graphic view of the file, they hide the extension. They hide the extension. So let me see. Let's take a look at the example. Okay. Let me show you one of the example. I have a file called bank account. Okay. Bank account is a Java document. So the extension is .java. But the file name, you don't see the extension, you see the bank account. Okay. So then when I try to compile the document, so I actually compile the document using the command line prompt. I use the command line prompt. Okay, let's see. I just go to the site. Okay. Let's see. Okay. So you can see that in here, if I use command dir, I can see the file is bank account.java, right? You can see bank account.java, but you cannot see this. You cannot see this using the Microsoft, Microsoft Windows Explorer. The Windows Explorer only see the bank account, but you can see the type. The type says it's Java file. Okay. Now, if I compile the file, I use Java C. Java. So I created a file called bankaccount.class. But .class is also an object file, but it's an object file, but it's also an executable file. Okay, so I can run this because Java is kind of different. They use the byte code. It's actually some kind of virtual machine, so they don't use the executable. But I can run this Java bank account. Okay. Okay, I can run this program. Okay. So I can see using Windows actually File Explorer. So they hide the file extension, but if I use the prompt, command prompt, I can still see the extension. Okay. So that's the file. And then there's another type of file. So this file does not contain any information about a specific one job. So it's called file directories. Okay. So in the Microsoft Word document, no, I'm sorry, in Microsoft Windows operating system, the file directories basically shows as a folder. So the file directory is a type of file, but it's not the file that stores your data. It's the file that stores other files. Okay, another files. Okay, so a file directory is a special purpose file that records information about other files and possibly other directories. Okay, so it does not contain a specific information, but contains the information of other files and possibly other directories. Okay. So there are various different format of the file directories. Several approaches exist to organize the individual file directories into a global directory structures. Okay, we're going to talk about various different structure for the file directories. One of the structure is called a free structure directory hierarchy. It's a collection of directories organized in such a way that every directory points to 0 or more files or directories at the next lower level. 2, every file and a directory except the root is pointed to by exactly one parent directory. So using file directory, you create some kind of hierarchical structure. Okay, so in that structure, you can put either a file, just an ordinary file, not the file directory, or you can put another file directory. Okay, so that's free structure directory hierarchy. Meet 2 conditions. Okay, so every directory points to 0 or more file directories. It could be actually over here and points to nothing. Now, at the next level, that's a lower level. That's a high level. Okay, and every file and the directory except except the root. Root is the top of the hierarchical structure. So that root doesn't have a parent, but the other directory has a parent. So for this directory, there's a point to exactly one parent. This one point to exactly one parent. Okay. So if this is a file, so file is under this root directory, and this is another directory, and then there's a file over here. That's a directory. Okay. Now, with the file directories, now you can actually specify a particular directory or particular file using something called a path name. Okay. One is called the absolute path name. The other one is called the relative path name. Now, if you don't understand the difference, don't worry. I'm going to explain using example. The path name basically tells you exactly where a file is located. So absolute path name of the file uniquely identified by the internal ID. Okay. The path name is actually uniquely identified the internal ID called F is the concatenation of a directory and the file names leading from the root to the file. A relative path name basically also tells the location of a particular file, but it's not from the root, it's from the current location. Okay. Now let's take a look at the example. To be able to navigate the hierarchical structure both up and down, the file system basically provides a special convention, normally used 2 dot to refer to the parent directory. Okay. For example, if you actually say CD, basically, just point to a particular location. But if you use CD dot dot, the dot dot basically means, okay, let's actually go to the parent directory. Okay. So let's take a look at this. Okay. So this file actually directory is actually typically used by Unix or Linux. Okay. Now at the top of this hierarchical structure, there's one file directory, one directory. It's called a root. Okay. Normally you use // Okay. That's a root directory. Okay. Now, in this root directory, they have 2 entries. One is called X. The other one is Y. 2 entries. Now, this entry is basically use the ASCII code to represent. So this entry basically is visible to the user. Okay. So it's using the ASCII. So basically it used the alphabet, the English language. For example, X could be, okay, my CSC 3100. Okay, I can use this. Okay, that's ASCII code. So that basically say, I have a directory. The name of the directory is my CSC 3100. So that's ASCII code. So it's visible to the user. The user can see this my CSC 3100. Oh, that's my folder. That's my directory. Okay. Now, that's the ASCII file name. Okay. Now, file while is another ASCII file name. File Y is the ASCII file name of the directory, but the X is actually pointed to a particular directory, which is R, which is called D2, D1. So X is an ASCII name, but the directory this direction the files the file X's internal ID is D1. So X actually points to D1. That's the internal ID. The internal ID is not visible to the user. The user only see X, which is, say, my CSC3100. But the file system use another name to represent this directory. That's a D1. So X is actually corresponding to D1. And the Y, which Y is corresponding to? Which internal ID that the ASCII name Y is corresponding to?
D2.
D2. So you just need to know that. That's the difference. Okay. So X point to D1, Y actually related to D2. And that D2 has three file name. That's also the ASCII name. So Z, R, T, these are visible to the users. Okay. And then Z actually points to D3. So the internal name for DZ is actually D3. Internal name for R is D4. Internal name for T is D5. Okay, that's the internal name. And then the D3 has one. And N, actually, N is the ASCII name, but it's pointed to the F4. So N is actually a file, the actual file. But M is also the internal actually ID is D6. So M is actually pointing to another directory. K actually also point to file. And this is a file. File. Okay. So basically you need to know the ASCII name and the corresponding internal ID. So for each directory, there's the ASCII name, which is actually visible to the user, but the file system use the internal ID to represent it. So you can think about this as the same thing. X is a D1, Y is D2. Okay, you can think about this, but the one is visible to user, the other one is invisible. Okay, so that's the file directory. And then next time we're going to talk about the operations for directories. Okay. Okay, I think that's pretty much all I want to talk about. Do you have any questions before we call it a day?
See you on Thursday, Professor. Thank you.
Okay, so thank you.
Have a good one.